Hello everyone, today we're going to talk about section 11.4, which is on three-dimensional figures. And this is going to kind of be an intro into the rest of chapter 11. We're going to start talking about a lot of vocabulary and some of the basic ideas of the things we're going to be continuing to discuss in chapter 11. So it's not super intense, but it's a great jumping off place. So to begin with, let's talk about some of these big vocab terms. Our biggest one for the day is polyhedron. This is a very general term for a three-dimensional solid. And the big things about these solids is that they're going to have faces on them, and these faces are called sides. Each of those faces is going to be a 2D shape, and when you put them all together, you have this three-dimensional shape. Now, polyhedron is not necessarily a term that I'm going to ask you to tell me. We're going to focus mostly on the difference between the two different kinds of polyhedron that we have, which are prisms and pyramids. So a prism is going to be a three-dimensional shape that has two bases. And typically when we talk about two bases, we mean it has one on the bottom and one on the top. And then there are going to be some other faces as well. And these ones are going to be around the middle. They're called lateral faces. So if you take a look what I have right here, I've got my two bases. I've got a bottom base right here and a top base right here. They're matching hexagons. All right, so then what's going to happen is that in between my matching hexagons, I'm going to need to connect them. And when I do that, I'm going to create some rectangles. And I'm going to have multiple rectangles running on the front, on the right side, on the left side, and even on the back. I'm going to be having some rectangles back there. And those are going to be those lateral faces, and they'll always be rectangles. Even if the bases are not hexagons anymore, it's still going to be a rectangle. Next, pyramids. Pyramids are going to have one base, and it's typically at the bottom. At the top, what's going to happen is that all the lateral faces are going to meet at a single point. And so you can see that I have my hexagon base once again, and then this time I have a single point up here at the top. When those other faces meet at that point, what ends up happening is that you end up with some triangles. So we're going to have triangles on the front, we'll have some more triangles on the right side and triangles on the left side, and then even triangles at the back to form that pyramid shape where you have that point at the very top. So you can tell if it's a prism or a pyramid by the number of bases that it has and the types of lateral faces that it has. And so you pick the way that you like the most. Try to become good at both. To extend this idea a little bit further, what if the base is round? So now in the case of a prism, if the base is round, then it's called a cylinder. So you have a circle on the bottom, another circle at the top, connected in between. That's called a cylinder. Same kind of thing is if you are talking about a pyramid. If the pyramid has a round base on it, then that's called a cone. Now the thing about cylinders and cones is that they're not actually polyhedron anymore because they have those curved edges. And so it doesn't get to be counted as a polyhedron. Polyhedrons have to be formed by polygons, and a circle is not a polygon. So that is a little bit different. Second, lateral faces. Sometimes people get a little confused about what exactly is a lateral face. A lateral face is going to be a face that's not a base. And so if you are talking about a prism, you're going to have two matching bases, and then everything else is going to be a lateral face. If it's a pyramid, you're going to have one base, and then everything else is a lateral side as well. That is even true if your drawings are sideways. So you can have a pyramid that points to the right or to the left. These are still the lateral faces here, and this is still the base, even though the base is not at the bottom. And the same thing for my hexagonal pyramid here, or prism right here. I have a base on the right and a base on the left, and my lateral faces are around the middle. All right, now let's talk about naming. So when you're naming these shapes right here, we're usually going to do it using two words. The first word is going to talk about the base itself, and then the second word is either going to be a choice between choosing prism or pyramid. So for our first picture right here, if you take a look, we have a base that we can spot up here at the very top, and it's not a rectangle or a triangle, and it has a matching same shape down here on the very bottom. That base shape is a pentagon. And so that is definitely going to be something that we're going to want to talk about and other people are going to want to hear about. So we're going to make sure that we include that as part of our name. It has two bases and the lateral faces are rectangles, which makes this a prism. Okay, to extend this a little bit further, typically when people are naming these, or when mathematicians are naming, they don't just call it a pentagon prism. What they do is they call it a pentagonal. They add a little suffix of al at the end there, and that tells you that it's pentagon-like. A pentagon would be a two-dimensional shape. This is three-dimensional, so this is going to kind of help it flow a little bit better and kind of bridge that gap between 2D and 3D. Second one, this time what we have right here is we've got a single base. Our single base has got 6 sides on it, very similar to what we've already been talking about tonight, and that means that it is going to be a hexagon. And this one only has a single base, and all of our lateral sides are triangles, which means that this is a pyramid. Once again, if you want to be as technical as possible, usually that suffix of AL is going to show up there. It is not a hexagon, but it is hexagon-like. Because it's not 2D, it's actually 3D. Now for our last one right here, if you take a look, there's a couple things I want you to notice. Thing number one, that there's a base at the top. That's okay. And that we are meeting at a single point down here at the bottom. That's totally fine. Second, our base. What kind of shape is our base? Well, our base is a circle. So what you could do is you could call it a circle pyramid, or maybe even a circular pyramid. That's actually pretty okay. But the best answer is going to be the most concise one. Any type of circular pyramid has been defined as being a cone. So our very best answer for this one is a cone. And it is probably what you would expect. It looks like it's ready for ice cream as it sits right there. Next piece. Next piece that I want to talk to you about is something called a cross section. What if you take one of these shapes, these three-dimensional shapes, and you take a very sharp plane, which is a flat two-dimensional surface, and you cut right through it, or you slice right through it. And when you do that, what you're going to end up with is you would slice it, and you would end up with two pieces, and they would come apart. And when you pull them apart, you would see a new fresh face, or a new fresh side, and that side would be a two-dimensional shape. And when that happens, I want to know what that two-dimensional shape would be. So if you take a look right here, I've got a couple of three-dimensional shapes, and you can see that the plane is coming through and slicing up that larger 3D shape. So we're starting off here with a cone. Now, a lot of times people are happy to associate cones with a 2D shape that makes them feel comfortable. And a lot of times that shape is a circle. You can see that when the plane slices through right here, that what's happening is that we're creating a small circle. And so that is actually going to be the 2D shape that is going to be on that fresh new face that happens after the slice. So that works out well. Second shape that we have right here looks like a cube. It looks like a 3D cube. The front and the right and the top and the bottom and the back and the left, they're all going to be the same square shape. And that means that a lot of times people are really excited to talk about cross sections with cubes because they want to use the word square. It's what they think is right, and that's what they want to use. If I'm looking at my cross section right here, I'm noticing that I've got a nice straight edge across the top. And I also notice that I've got a couple of other straight edges coming down the sides here. Now, what I'm also noticing is that they look like they're getting narrower as they go down. And then also at the bottom, you can see that we have a chop going across the bottom right there, which also looks pretty short. And so because of that, I don't think that that's actually a square. It's not a perspective issue or an optical illusion. What we're looking at right there is actually a trapezoid. Probably an isosceles trapezoid, but to be safe, I'm just going to call it trapezoid. It is okay to not just go with the first initial gut feeling. When you see cube, a lot of times people want to say square, but it is possible to get a cross section of a trapezoid or a parallelogram or a triangle out of a cube. So you have to kind of really analyze what you're looking at right here. Last one. Last one's a pyramid. It is a triangular pyramid. It has a triangle base down here at the bottom. The plane is going to come, and slice it right above that base. And when it does slice it, it looks like it's pretty much parallel to the base as well. And so when you see that slice, what you're going to see is you're going to see that you have, once again, another triangular shape. Might not be the exact same triangle. Could be a little smaller. Could be a little bit stretched out in some kind of way. But it is definitely a triangle. These diagrams right here are not perfect, but they're about as good as they're ever going to get. So if when you're looking at that, you don't see it exactly the way that I see it. I want you to try to just keep practicing with them so that you can kind of fill in those gaps. If you don't feel like it's satisfying exactly the way that you want it to, I don't know that it ever will. And so we're just going to try our very best so we can get comfortable with it, even if it doesn't look the best way that it possibly could for you. Let's extend that idea a little bit further. So if you take a look right here, what we're going to do is we're going to start off with a very limited drawing. And I want you to see if you can take that limited drawing and produce a little bit of a richer idea in your mind. So what we have right here is we're going to start off with a 2D shape and an axis right here. And what I'm going to ask you to do is I'm going to ask you to revolve that 2D shape. And when you make that revolution, what's going to end up happening is you're going to end up with a 3D shape. What I like to do is I like to pretend like this axis that is marked off is a string that is this has this 2D shape attached to it. And I like to pretend like I could hold on to either end of the string and spin it by moving my fingers back and forth and then thinking about what would it look like if I spun it fast enough so that you could see it on the top and on the bottom, on the left side and on the right side, all at the same time. And so that's exactly what we've got going on here. This is just a basic rectangle, but if I could spin that rectangle so that it would spin out towards the front, oops, and if it could spin down towards the bottom, and if it could also spin towards the back as well, all at the same time, what you would end up doing is you would see that that is actually going to spin out into this shape right here. That same rectangle is represented at the top and at the bottom. It's represented at the front and at the back, all at the same time. That's a cylinder. That circular motion has built a base that is a circle on the far right side and on the far left side, and that means that we have a cylinder connecting that base together. Same kind of thing here. We're starting off with a very basic right triangle, two-dimensional shape, but if I could put my fingers on either side of that pretend revolutionary axis or that rope, and if I could spin it really fast so I could see it on the left side and on the right side, on the front and on the back all at the same time, what would it look like then? And what's going to end up happening is that it would spin so fast that you would create this circular base down here on the bottom, and you would end up meeting at that point on the actual axis of rotation right up there at the top. That's a cone. So then the question becomes, what about this third guy? Take a couple seconds to see if you can decide what that third one is going to look like if we could spin that one so it showed up at the top and on the bottom, on the front and at the back at the same time. Well, this guy would end up being three-dimensional, and we would have that same kind of semicircle hemisphere down here at the bottom, and then you'd also have that hemisphere showing up on the front and at the back all at the same time. This guy right here is going to end up being a sphere. So there's a couple of different ways to kind of think about these three-dimensional shapes, ways that you may not have thought about them in the past. Let's see if we can jump into some actual calculation. So on the back side right here, what you're going to find is you're going to have an opportunity to kind of compare some of these three-dimensional shapes. And so that's what we're going to kind of do our calculation with today. So if you take a look, what we're going to have is we're going to have a couple of three-dimensional shapes that are definitely close to each other, but not exactly the same. When you've got these types of shapes right here, we're going to call them similar solids. And what they're going to do is they're going to have equal ratios of corresponding linear measurements. So they won't be the exact same, they're not going to be identical, but they're going to be equal ratios. So that means if you take a look at the height over here on this one and the height over there on this guy right here, no, they're not the same, but that ratio of heights, if you built it into a fraction, would match another ratio of maybe a radius over here and a radius over here as well. This is a really good similar set right here. When the height got taller, so did the radius. The radius got longer as well. For our second set right here, you'll notice that this has non-similar, because this is actually a really bad set. You can definitely tell that there is a larger cylinder and a smaller cylinder, but I also want you to notice that even when the radius goes from being smaller to being larger, the height doesn't. So we start off with a pretty tall cylinder to begin with, and we end with the exact same height. That's not okay. If one dimension changes, then both of them have to change. And if both of them don't change, then it's not similar. They might still be the same shape, cylinder, but they're not similar cylinders. Let's see if we can identify some similarity in some prisms. So what I have right here is I've got a pretty small little prism right here. I would call it a rectangular prism. And I want to match it with one of these two prisms right over here that it's going to be similar to. Not the same as, but similar to. Now, what I've noticed recently is that students have a pretty good gut feeling. And so even before they've calculated anything, they already have a good idea about which one is going to be the better match. And so if you're looking at both of these, you might be already feeling your choice has been made as well. This one right here seems to be the preferred choice, and it's backed up with some work. And I do want to see that work. So you're not going to just be able to use your gut and then call it a day. We're going to need to make sure that it actually works out well. So let's match up some stuff. One of the things that I want to start off with is this width that's going across the bottom right here. I'm going to match that up with another width that I have right there, and I want to build a ratio. Now, when you're building this ratio, you can do it any way you'd like. One of these numbers has to go on the top of a fraction, and the other one has to go on the bottom, but it's really your choice. I'm going to choose to do 5/10. But you could also do 10/5. 5/10 reduces, which is great. And so I'm going to reduce that guy, and it's going to give me 1/2. Let's do another one. So now my second value that I want to take a look at is going to be this depth that I have right here, which is a depth of 3. And I have another depth right over here, which is going to be a depth of 6. These need to form a ratio as well. And this ratio reduces. Last one that I want to take a look at is the height. So right over here, we've got a height of 7, and over here, we've got a height of 14, and I want to build a ratio with that one as well. I am always doing small on top and big on bottom because that's what the first one was. So I just want to stay consistent so I don't change it up at any point in the problem. 7 over 14 reduces as well, and we end up with 1/2. Now, if you're looking closely, or probably not even looking closely, you'll probably notice right away that all the ratios are the exact same. And because those ratios are the exact same, that means that these two shapes right here are similar. Now, I was careful. I went through all my calculations. They all matched. They all worked out well. And that's how I know that they are going to be similar. If you're looking at that second set right there, it's pretty convincing. If you start off with your same width value, you have your 5 and a 15. Now, 5s and 15s play very nicely together, and they reduce really nicely as well. That's going to reduce down to 1/3. And if you look at your depths, again, we have 3 and 9. And you know what? 3 and 9 work really nice as well, and you get another 1/3. So this one's looking great too. And for our last set right here, for our heights, we have a 14 and a 7, and that also plays really nicely together. If you're in a rush, you might just be convinced that they're both similar to the original smaller prism, but it doesn't actually turn out to be the case. 7 over 14 reduces, and when it reduces down to 1 over 2. That's not the same, and because that is not the same, that means that this is not similar. So not as good of a situation right there, which you probably had a gut feeling about to begin with. So this one is the good one, and this one is the bad one. All right, your turn. So I've got two sets right here, and I want you to decide which one is going to be, once again, the good one and which one's going to be the bad one. Each of them has a smaller shape and a larger shape, and so you're going to have to kind of do some comparisons. Cones. For our cones right here, we've got some radius values that we can compare and some heights. When I compare my heights, I get 4 over 10, which reduces down to 2 over 5. When I compare my radius values, I just get 3 over 5, and it doesn't reduce. It's just 3 over 5. 2 over 5 and 3 over 5 might be close, but they're certainly not exactly the same. So that means that these are not similar shapes. Second set. Second set initially looks like it's also not similar because, once again, you have these matching 5s right here. And so just like up here at the top, when we were talking about the heights for staying the same, and that was actually bad, it looks the same kind of thing here. There is one subtle difference, though. If you take a look at the first 5 right here, you'll notice that it's pointing at the center, which means that it's actually a total distance from the far left to the right, which makes it a diameter. The real radius for this problem right here is actually 2.5. Now, if we use that radius and then another radius, you can build a fraction that does reduce, and it reduces down to 1/2. And the same kind of thing happens with the height. Our height right here is 7.5, and our height over here is 15, and those reduce down to 1.5 as well. And so that makes these two ratios identical, which means the shapes are similar. It's tricky when they add in these subtle details. The work is usually not very tricky, so they're going to try and find some other kinds of ways to kind of keep you on your toes. Now, these linear dimensions, these distances that we've been taking a look at for these problems, are not the only ways that you can compare two three-dimensional shapes. And so I've got two more that we're going to talk about as well. These two shapes are also going to kind of dominate our chapter. We're going to spend a lot of time talking about the next two pieces right here. And those pieces are surface area and volume. So now surface area is going to be the sum of the areas of all the faces. So if you had a three-dimensional shape, and if you could take the front off and the top off and the bottom off and the left side and the right side, if you could take all those pieces off and then find the area of each of them and add them up, that would be surface area. So if you take a look right here, I have a three-dimensional cube, and I'm taking off all of the sides, and I would find the area of each and add them up. That is going to be surface area right there. Volume, on the other hand, is going to be the amount of space that is occupied by a polyhedron. So that means if you filled it up with water, or in this case right here, if you take a look, what I've done is I've kind of filled it up with cubes, and I've got more cubes that are coming in. And if we could count exactly how many cubes it was to fill this shape up all the way to the very top, then that would tell us what the volume of this shape is going to be. And so that the surface area is all about the outside, and then the volume is all about the inside. Now, if you want to use that similarity that we were talking about earlier with surface area and volume, you can. It works great. But they're a little bit more complicated, so you have to add on a couple of extra pieces. When you're calculating surface area and you're using units to write down your final answer, your units are going to need to be something like inches squared or centimeters squared or feet squared. And so if you are creating a ratio using surface areas, then that ratio is going to be equivalent to your linear distances as long as they have been squared. Same kind of thing happens for volume. When you are calculating volume, your units for your final answers are going to be something like inches cubed, centimeters cubed, or feet cubed. And so if you are creating a ratio of volumes, it is equal to your ratio of side lengths, but that ratio of side lengths must be cubed. This is really easy, and a lot of times people look at this and they say, yep, that makes perfect sense. I've got it, Mr. Slomka, I won't forget. And I agree, I think it is super easy as well. But a lot of times when kids are in a rush, they just never actually do it. It's just something that never crosses their mind. They go through all the steps, they feel great about it, and it's just never something that they actually take advantage of. They never use their powers of 2 or their powers of 3. So that's the main thing I also want to point out to you is make sure that you're being careful. Watch out for those opportunities. Whenever you see those words surface area, you need to think about powers of 2. And when you see volume, you need to think about powers of 3. Let's take a look at a couple. So for our first one right here, it says we have 2 cones, and it says find the volume of the larger cone. So if you take a look right here, I'm looking for the volume. It would be great if I could just look at the picture and calculate the volume, but we don't have a volume formula yet, and we don't even have enough information to calculate the volume. So what I'm going to use is I'm going to use the fact that both of these cones are similar. So now on the last couple problems, we had to do a lot of testing to determine if 2 shapes were similar. This time I'm just telling you, I'm going to tell you these 2 cones are similar. You can trust that fact. So I'm going to use that. I'm going to build myself a good ratio of lengths based off of what I can find that is a nice match set in these cones. This ratio of lengths is also sometimes called the scale factor. I notice that I have a height right here in my first cone, which is 9, and I have another height in my second cone, which is 12. So I'm going to build my ratio based off of those 2 numbers. They also reduce, and so I'll reduce those guys down. 3 looks like it's a good common factor, and this is going to reduce down to 3/4. Okay, so now if I want to find this volume right here, I can do that because these shapes have so much in common, even if they're not the same exact size. And so I'm going to use my scale factor, which is 3/4, and I'm going to build another ratio with my volumes. Now the smaller cone had a volume of 108, so I'm going to write that 108 in my second fraction, and I'm going to put it on top with my smaller number. My larger cone is the one that I don't know the volume of, so that's the part that I'm going to be solving for right there. Okay, so now it is at this particular point where a lot of people start to put 2 and 2 together, and they already have got 3 more steps planned out, and they know exactly what to do next. And they're like, well, I'll just do this and this and this, and I'll have my answer, and I can go on to the next question. And I agree. We have 2 fractions that are equal to each other, and we've done this type of problem 1,000 times before. And so you have a good idea, and that's great. But the one thing I want you to make sure that you're being careful about is that you're taking into account the fact that this is a volume question. And so what we have over here is lengths, and we have volumes over here, and they don't match very nicely. So in order to get them to match, what you need to do is you need to include those powers of 3. That probably wasn't the idea that you were having for the next step, but it is the correct one. You do need to put those powers of 3 on there. All right, let's use it. So now I'm going to use those powers of 3. This is something I want to type into my calculator. So that would be typed into my calculator using a button that is called the caret button, and it looks like a little arrowhead. Then after the caret button, you can tell it whatever power you want. So I'd be typing it in with another 3 for my power, and then I could hit my enter button after that. 3 to the 3rd power is going to be 27. 4 to the 3rd power is 64. Okay, so now that everything is cubed over here on the left side, now we have some 2 fractions that can be equivalent to each other. So this is going to look a lot nicer, and now you can do what you wanted to do. Most people are very quick to say, this is a great opportunity for cross multiplication, because it is. And so we're going to cross multiply, and that's going to really be helpful. So our first one is 27 times v, which is just going to be 27v. And our second one is 64 times 108, which we're going to plug into our calculator, and it's going to give us 6,912. One last step in order to get a final answer. We're going to get the v alone by dividing by 27. And when you do that, your v value is going to be 256 centimeters cubed. I needed a volume that was bigger than 108. I didn't want it to be much bigger than 108 because 12 isn't much longer than 9. So 256 feels pretty good. I'm happy with that answer, and I'm going to move on from there now. Here's a U-try problem. This is going to be the same kind of thing. I've given you the scale factor this time, and I'm going to ask you to find the surface area of the second prism. So our surface area is once again 5:2. Now that's a great way to type it if you're trying to write out a ratio inside a Word document, but the way that we work with it is usually a fraction. So I'm going to write it as 5/2 instead. Then I'm going to take my fraction of 5/2 and set it equal to my surface areas. My prism A had a surface area of 96. Prism A is the larger prism, so I'm going to put the 96 in the top with my 5. Prism B was the smaller one, so I'm going to have my variable in the bottom with my smaller number 2. Now the big thing is, once again, this is a surface area question, so when you're working with your 5/2, make sure you square them. That's going to give you 25/4. Now you can cross multiply, and when you cross multiply and divide, you get 15.36 feet squared this time because it is surface area, not volume. All right, one of our last examples that we have right here is this one about 2 balls of string. We have a store and they sell a large ball of string and they sell a small ball of string as well. The diameter of the large ball of string is 1.5 times larger than the small ball. And the prices are different as well. The large ball sells for $4.99 and the small ball sells for $1.50. Okay, so then the big question becomes, which one's the better buy? So should I buy maybe 1 or 2 large balls of string for $4.99 a piece, which is going to take me up to $10? Or should I buy a lot of small balls of string? I'll end up with the same amount of string both time, but maybe I'll spend less money if I buy the small balls. Or maybe I'll spend less money if I buy the 2 big balls. And so we have to make that choice. And the way that we're going to do that is by calculating. All right, so one of the things that can be tricky about this problem is the way that they've kind of started you off. They tell you that the larger ball is 1.5 times bigger. So if I knew the diameter for that small ball, I would take that diameter and I'd be able to create it once, and then I'd also have another half of a diameter in there as well to create the diameter of the larger ball. Okay, so now the problem is that I don't know either of those diameters. It's unknown to me. So one thing you can do is you can just kind of make it up. You can say, well, what if the diameter for the small ball was 1? That's a nice, easy number to work with. What would be the diameter of the large ball? Well, 1 times 1.5 happens to be 1.5. So that's a really nice, easy way to kind of get you started. And so that's something I would recommend that you do. And you can use it to build your ratio as well. I'm going to build my ratio with my 1.5 and my 1, and that's going to be a great way to start. I'm also going to build a ratio using my prices. So my larger ball that had a diameter of 1.5 also has a larger price, which is $4.99. And my smaller ball that has the smaller diameter has the smaller price of $1.50. Okay, so now here is the big question time. My big question for you is going to be about this ball of string. And my question is, when you are wrapping string to create a ball, are you wrapping it in a surface area way, or are you wrapping it in a volume way? Surface area would mean that there would be some sort of piece in there that you would wrap around, like a spool when you wrap thread around a spool. So there would be some kind of maybe hollow internal piece that you'd wrap the string around. Volume would be more like if you started off with just a little tiny knot of string and then you wrapped around it and around it and around it, and you put string on top of more string on top of more string until you had a ball of string. And so in this case, what we're really talking about is probably that. They didn't talk about any kind of spool or hollow center. So we're going to assume that this is a volume question, which means that we do need to include our powers of 3. So we're going to put our powers of 3 on there. Okay, so now that you've got your powers of 3, we're going to cube this. This is going to give you 3.375 over 1. Okay, so now that's a step that a lot of people would be happy to overlook. They're just not interested in doing it. They don't think about volume because volume was not written down in the problem. You have to do a deep dive in order to even determine that volume is part of this question. And that's an important piece that I want you to try to get comfortable with. Now that you've done that, though, you should be able to kind of cross multiply and make a choice. So now here's my last little piece that I'm going to do for you. What I also want to do is over here for our prices, I've gotten both my prices written down. And if you notice, I don't have any variables at all. And so what I'm actually going to do is I'm actually going to pull out one of my prices. You could pick whichever one you want, but the one that I'm going to choose to pull out is I'm going to pull out the $1.50. And here's what I'm basically doing. I'm going to pull out the $1.50. I'm going to replace it with the variable X. And the reason that I'm going to do that is because I'm going to calculate the value here for X. And if it calculated out to be $1.50, that would show me that the way that they're setting up their prices is similar to the way that the actual volume of the ball of string is. But if the price is a little bit higher or lower, then that's going to show me that I'm either getting ripped off or that I'm getting a better deal. So I'm going to be able to determine what I get here, and then I'm going to compare it against the $1.50. So I don't have to use the $1.50, but I'm going to compare it to it. So let's do that. So when I take my 3.375, I'm going to multiply it by x this time, which is going to give me 3.375x. And when I do 1 times 499, I'm still just going to get 499. All right, then my big move right here is going to be to do my division. And when I divide by 3.375, that is going to give me my new price for my small ball. And I want to compare that against the $1.50. So when you do the division, you don't get a $1.50. What you do get is 1.48, which means that what they really should be charging, what the shop should be charging, is $1.48. But they chose not to. What they did choose to do is they chose to bump the price up a little bit and make it 2 pennies more, which is $1.50. So they're ripping you off. The amount of string that you get is worth $1.48, but they're asking you to pay extra money in order to get that string for the convenience of having a small ball. So this is not a good buy. It's too expensive. If you bought a lot of small balls of string to be equivalent to a couple of large balls of string, you would have to spend extra money. So that's not the good choice. This larger ball of string is going to be the better choice. You'll pay less money for the same amount of string. Last one is a U-try problem, and it's similar to this. So what we have is we've got 2 surface areas, and what we want to do is we want to see if we can come up with a scale factor. Now remember, a scale factor is going to be a ratio, and typically it's a ratio of side lengths. We don't have any side lengths in the picture right here, so it would be difficult to find it. You're going to need to use surface area in order to find the scale factor. I've taken my 2 surface areas and I've stacked them into a ratio. I chose to put the 72 on top, but you could have put the 288 on top. Now, because it is surface area, that really means that both of these values have already been squared. And you can see that really easily in the units. They're both saying meters squared. When I want my scale factor ratio, I really want it to be a meter value over another meter value, which means I need to remove the power of 2. So my option for doing that is to use a square root. Now, I don't take the square root right away. If you take a close look, what you'll notice is that I'm actually going to start with these large numbers that are in the fraction. 72 and 288 can be reduced, and that's going to make your life a lot easier. So whenever you can reduce, always make sure you take advantage of that as soon as possible. So now the fraction reduces down to 1/4, and now I'm going to take advantage of my square root. So I've saved it until it was a little easier to work with. If I had taken my square root earlier, that would have been fine, but you would have had some ugly decimals, and you would have had to fight through using those ugly decimals, and it wouldn't have been as easy. Simplifying early makes the problem a lot easier to work with. Simplify early, simplify often, and you'll be a happy mathematician. Okay, so we talked about surface area, volume, and similarity, and we also discussed a lot of vocab, such as vertex, edge, surface, face, and cross-section, and solid of revolution.